Chapter 8.2 General Projectile Motion 1. Projectile launched at an angle. Normally, projectiles are projected at an angle with the horizontal. The horizontally projected motion that you have studied in the last chapter is just a special case. For general projectile motion, the vertical and horizontal motions are still independent of each other. Therefore, the trajectory of a general projectile motion is a resultant of horizontal uniform motion and a vertical accelerated motion under gravity. In other words, we may use the equations of uniform motion for horizontal component and equations of uniformly accelerated motion for vertical component of the projectile. In this way, we may find the horizontal and vertical components of displacement, velocity, and even acceleration easily using these equations from 6 to 10. By the way, there's no need to memorize these equations, as the equations for uniformly accelerated motion, as listed on page 61, will be given in an examination. Using these equations, we may find the time of flight, t, the maximum height reached, h, and the range, which is the maximum horizontal displacement, r, of the projectile easily. For the projectile making an angle theta with the horizontal on a leveled ground, the expression for t, h, and r are shown here on the right. We may try to verify these formulae after this video. Nevertheless, a projectile is often projected on a special landscape. As for figure 8.2c, which is not a leveled ground, and when we apply equation 9, we have to put Sy equals -5 meters, as the mass will have dropped at a height of 5 meters in the projectile. In example 4, you have to find the time for the ball to reach the highest point. You have to know that at the highest point, the vertical velocity is 0, and therefore Vy is 0 when you apply equation 8. 2. A special case. When the projectile is launched on a leveled ground, the trajectory is symmetrical. The time for upward flight will be the same as time for downward flight. The speed of the projectile will also be the same at the same height, at A and B here in the diagram. And the directions of velocities are also symmetrical as shown. And for the range, which equals u squared sine 2 theta over g in this case, depends on the angle of projection, theta. And let's take a look of the following simulation to see how the range changes with increasing theta. For the initial speed of 18 meters per second, let's start from an angle of projection 15 degrees to find the range. The range is only 16.5 meters. Let's change it to 30 meters and see how the range may change. It's longer, as you can see. Now let's make it 45 and see what the range would be. And you can see that's even longer. So let's make it now 60 degrees without changing initial speed. And that's interesting, that it will produce the same range as it is for 30 degrees. And now let's try 75 degrees. So we go very high, and then when it falls, it produces the same range as for 15 degrees. So you see that the maximum range is attained at when angle of projection is 45 degrees. And a pair of complementary angles, such as 15 degrees and 75 degrees, will produce the same range. The following experiment may verify the above observations. This setup is used to study the relation between the range and the angle of projection of a projectile. Attach a long stick parallel to the end of the hose. The stick indicates the angle of projection of water projected from the hose. Use a protractor to measure the angle of projection. Make sure the hose is placed at the center of the protractor. Now set the angle of projection and observe the range. Turn on the water tap slowly. Measure the range from the meter ruler. Vary the angle of projection from 30 degrees to 45 degrees to 60 degrees and 75 degrees in turn. Observe how the range changes with different angles of projection. So this is obvious that the angle of projection equal to 45 degrees will produce the maximum range. And one very important precaution of the experiment is to keep the water flowing at a constant rate. In example 5, a motorcycle took off from a ram and attained a maximum range. You are asked to find the maximum range. First, you have to convert the speed and express it in meters per second. Then you have to calculate the time of flight easily. In part C, the question asks why the motorcycle should land on a ram. And of course, you may probably give a reasonable explanation. Check it out. And now please do check point 3 on the next page.